welcome everyone for this new Flow seminar. So for those who might be newcomers, so Flow is a general seminar to discuss the latest scientific results in federated learning. We are trying to have a broad perspective on different aspects like distributed optimization, learning theory, privacy and security like today, personalization, compression, systems, and of course applications. So I'm Aurélien, and I'm one of the co-organizers, along with Peter Richter, Virginia Smith, Dan Alistair, Samuel Orbat, and Sebastian Stitch. All right, so before I introduce today's speaker, just a quick recap of how to ask a question. So Jonas has accepted to, says he preferred that you ask any questions you may have during the talk, which I think is good and makes things more interactive. So please don't hesitate to interrupt. So all mics are off by default, but you can raise your hand using the raise hand features, or just write the question in the chat. And yes, if necessary, we can just turn on your mic so that you can ask the question yourself. And that's it for logistics. So our speaker today is Jonas Geiping. Thanks a lot for accepting our invite. So Jonas is a postdoctoral researcher at the University of Maryland, College Park. He received a PhD in computer science in 2021 from the University of Siegen in Germany. And he's working, broadly speaking, on optimization for machine learning, and with some focus on the implications of that for the security and the privacy of machine learning systems. And today he will be talking about privacy attacks on federated learning. So typically attacks that aim to reconstruct some of the private data at the clients from the gradients or the updates that they share. And in particular, I think he will kind of discuss and challenge this honest but curious server assumption that was taken in previous work on such attacks, and show that in situations where the server acts maliciously, much more powerful attacks essentially are possible. So looking forward to that. And Jonas, floor is yours, and thanks again for giving the talk.
Yeah, thank you so much for the introduction. And yeah, everyone, welcome to this talk. This is new threat models for privacy attacks and federated learning, and I'm Jonas Geiping. And what I'll be talking about today, just to give a brief overview. So I'll be talking very briefly about what I mean by federated learning, but I won't torture you guys so long with that. But we'll talk more about a user-centric privacy, a user-centric outlook on privacy in federated learning. And then we'll discuss what this means and what privacy means in federated learning here. And then we'll talk about two threat models that I find interesting from a perspective that these are more realistic and more user-centric, and these will be malicious architectures and malicious updates. And we'll spend most of the talk on that. In the end, there'll be some time for conclusions and questions, but please interrupt me anytime when you have any questions. I think it'll make the talk usually much more interesting. All right. This is joint work with a bunch of co-authors, where I want to highlight especially Liam Fowle and Yuxin Wen, who are pictured here on the side. All right, so what is federated learning? You guys are probably the most aware of what federated learning is. And so I won't go over this picture too much, but I think we should still focus our notation. So in this talk will be entirely about systems with a single server and a group of users. For example, here in our popular example, we have a bunch of devices, but we'll only talk about a single server and a group of users in this talk. And we'll formalize our notation in the following way, where we'll have some loss function, L, and we'll have some parameters. These will always be theta, and we'll have data xy. And for a centralized server, you can write down a stochastic gradient descent in this way. And then, of course, for federated learning, you could split this up in interesting ways. For example, here is how we would split up for a federated SGD. But there are, of course, many ways to distribute this computation. For example, also we have federated averaging or many other schemes. This talk will mostly focus on federated SGD, just for simplicity, but most of the things in this talk will carry on to other optimizers. But please ask me about this if you have questions about other optimizers. And of course, here the key things are that the server can train our model and update our parameters theta, without having access to the data points X and Y directly. And there's of course the idea here that this is just gradients, that gradients contain only the information that's necessary to update the model. And there's inherently less information in these. And you can already guess that this is what our talk will be about. So is federated learning private? Federated learning is definitely very often private. And the big thing though is that like sometimes it might not be. And this is what this talk will be about. This is a quote from, I think this is the Wikipedia page of federated learning, where it says, okay, the main advantage is data privacy, data secrecy, but it's not always so easy and it's not always guaranteed. And the main question here is that basically, if a user has some local data, let's say this picture of a dog, puts this data through a neural network and gets an update, here a gradient, the system is only as secure as no one can recover the data from the gradient. As soon as this is possible, then the system can be inverted and the privacy is broken in this system. So why is user-centric privacy interesting? So what we mean by user-centric privacy is we'll talk about protecting the private user data from the knowledge of the server. So the attacker here will always be the server, so the party that's training the model, and a defender will be the user or the client device that actually owns the data. And there's a lot of work in federated learning, basically from the server perspective, on how a server would train optimally and how a server would best orchestrate the system. But we feel like there should be more an eye on the user perspective, because the user perspective is usually at a disadvantage in both knowledge and compute, because in the end, what the user devices do has to be decided beforehand, and the user devices cannot decide this really, and we can't expect the user to really be involved in federated learning research and choose the safest thing for their client device. These client apps have to be fixed and automated, so we should figure out what's the way to make them secure. And why we like to use user-centric privacy is because there's a lot of federated learning right now, but in the future we might also want to question if a party that wants to run federated learning is really interested in running user privacy, especially with upcoming laws that are implemented, for example, in the European Union. It might be advantageous for companies to run federated learning, but not really do it. And so this talk will be about the question of like, if you can do federated learning, but not really do it and rather skim off some user information on the side. And of course, this is not all, even if you believe that the party that orchestrates the server is always genuine and honest, then you should still be worried about this, because servers can be compromised. And we would like these systems to be future-proof and to never leak any data, even if the party that controls the server changes at some point in the future, even if briefly. So what's the threat model that's usually employed in literature? So the usual threat model is that of an honest but curious server. So what that means is that the server is honestly training a model of federated learning. So the server upholds the protocol. The server initializes the model normally and sends it out normally. The server can, though, store and separately process user information. And in this way, the server is curious about user information. But the server does not maliciously modify the model architecture, send fake parameters, or modify the algorithm. And there's been a good amount of work on attacking privacy in this honest but curious setting. And what attacking privacy means here really is like evaluating the question, in what scenarios can a server recover user data if the server is honest but curious? And a lot of this talk will be about larger ML models and large machine learning models. And basically because there it is easier to do these attacks, especially for very small applications with just a few parameters that are exchanged between server and client. These attacks are hard. But the larger the model is that is exchanged, the more likely these attacks can become. Okay, so in the honest but curious setting, before we look at some attacks, I think it makes sense to figure out theoretically what's the simplest case where this can be thought of to work. And the simplest case is a linear layer somewhere in a model. And we can just do this computation very briefly because I think it's very insightful. So if we have a linear layer, so a linear computation with a weight and a bias somewhere in a machine learning model, let's say a neural network, then we can actually always compute the input to this layer from the gradients of the weight and the bias. And this works in the following way. Let's say we have a linear layer, Wx plus b, and a loss L. Then we can compute the gradient of W, and we compute the gradient of B by the chain rule. But the interesting part here is that the gradient of both with respect to the output, which is the gradient of the loss with respect to Y, is repeated in both the weights and the biases. And here the bias loss here is just a scalar. What this means though is that we can easily divide the gradient for this row by the same bias value of the same row, and then we recover the input to this layer. And what this already means is that if you have a model that only consists of linear layers, then you can just compute it all the way to the beginning and compute the input directly to this model. So this is sort of a simple scenario where you can always recover something. What's however also important for this scenario is how this would interact with aggregation. So here, this is written down for a single data point X. If you had a gradient that consists of multiple data points, then you could only recover the average of these multiple data points, which gives some security in some applications. So, but many attacks don't work by this scheme because it's actually, there's a minus missing here, but please think of the comma as a minus. For many attacks, you have a more general model that's not just linear layers. So what you could do there is you could run these attacks just via optimization. So you optimize this objective, or you optimize a similar objective, where you basically just try to match the user sent data with your own model of the gradient. And you can backpropagate this and optimize this objective as sort of an adversarial attack. And this can actually recover a bunch of data in some scenarios. Here, this is an image classification model. This is a ResNet, where the left image is the input and the right image is the recovery. So these attacks can actually work. And there are a bunch of other attacks in this scenario on honest but curious, on which I don't want to go focus too much on in this talk. But these attacks also exist, for example, for vision transformers and other systems. What's interesting though is that these attacks are in some ways very limited. For example, even for large computer vision models, these attacks usually can't recover a batch size larger than 64 on a user side, or like they can't recover a large aggregation of user data. So a secure multi-party algorithm like secure aggregation can actually defend against many of these attacks just by aggregating a lot of user data. Once a lot of data is aggregated, then this optimization will be very hard to solve and will not recover a lot of useful user data. So that's the scenario of honest but curious, which might lead us to think that aggregation is basically enough to defend against these attacks. So let's now talk about some other threat models that I think are a bit underappreciated in literature so far. So the first question here is that, is the honest but curious threat model actually realistic? And for that, we have to ask some questions. For example, who actually chooses the model architecture that's used in the system? Who has control over the server? Or how much code can be executed on user devices in general? And if we come back to our previous picture, of course, that from a user perspective, you are just one phone in this group of things. And there is like, from the user side, there's no control over what goes into this phone. So what update the server sends. The user side only controls the output of their own device, and they control their own device. But they really have no control over what's sent to their device. So what we think is much more realistic is actually a malicious server threat model, where a user should not need to trust the state sent by the server. So the state here is a catch-all for the settings of the system that the server sets up and sends to the users. So a way to think about this is that the server state that is sent to the users, for example, the model parameters theta k, is like sending some untrusted code that will be executed on the user data. And this is less true for very small models, but especially for larger models, for example, like small language models that are running on your device to do next word prediction, these models are actually very expressive. And what the function that these models describe is basically described by the parameters that are sent from the server. So if the server sends a different parameters, then these models now execute a very different function. And in this way, these models execute an untrusted function that the users don't know about directly on their data. And that's why we think this malicious server model is actually more realistic. And there are some, like, why is this most realistic? And what do we mean by it? So to formalize this malicious server threat model, in this model, still the users and servers both uphold the Federated protocol. The user still downloads the server state and computes their update, for example, a gradient or a Federated averaging update is normal. And the server collects these updates as normal. The only difference is that here now the server can send an update that is actually malicious. And the server can send parameters theta k that are not designed to classify anything, to do any task. They're only designed to attack this one user and then can be discarded afterwards. And why is this realistic? An interesting thing here to think about is that there could be a stronger threat model. Like, for example, you could ask, like, if you allow this, why don't we allow the server to just run arbitrary code on the user side and just download all the data? And the answer is, of course, that all the questions of stronger attacks, for example, of code execution by the server on the user side, these can be defended against with known software and hardware tools. For example, we can do sandboxing, and we can have an open source implementation that's verified. So the server can't just have a code that says, okay, have an HTTP download of the user's data. We can defend against all these scenarios, and we can actually look at the user side code and make sure that there's nothing there except for the federated learning application that just computes the update. But the problem is that the attack is only based on the updates theta k sent by the attacker. So this attack still works when there is only when all these security measures are in place. That's why we think this malicious server model is very interesting. And of course, there's a question like, my company wouldn't do this, or my system wouldn't do this. But this is still important because even in the future, the system could be compromised, and then it could send out malicious models in the future, or when it is breached by someone or sometime in the future. And this is further important for setting up third-party APIs, because, for example, we might want to train our models collaboratively, for example, in a big consortium of universities. And here's a big question of, like, who owns the data and who can decide the model that's used during training, and who can orchestrate the system and set up parameters. And if these systems are not set up in the right way, then one of the parties can just abuse the system and recover the other party's data. And what's also important here is that, of course, this attack can be very targeted. So a server can actually send malicious states to only a few users, and then just discard them from the averaging and just train as normal. And the server can train like this as normal for many rounds of federated learning or many applications, and then just once run an attack and then not use the attack's data except to recover the user data, and then just continue as normal. So the first variant of this threat model I want to talk about is malicious architectures. And this is the question that comes up here, is that does the server state include the model architecture? And where is the model architecture defined? And because if the server controls the model architecture, then our question really is, what is the minimal change to an architecture that can breach privacy? And this is basically related to our work on robbing the Fed, obtaining private data and fed learning with modified models. So we really asked if the server controls the model, because as they currently usually do, because usually the person who wants to train the model also decides what model is being trained. What's the most damage that this can do to a system? And the interesting thing is that this is actually very easy to do, because we've seen earlier that we can recover the inputs to a linear layer. The only thing actually that's necessary is to insert a linear layer early into the model. So even in a model that has a linear layer early or after the inputs directly can work directly But even a model like a convolutional neural network, you could maliciously insert this layer. And then we can run an attack that we described in this paper, which is based on imprinting. And I have to go a bit more into detail onto this attack. So how does this work? So first we have a batch of data. So can you see my cursor actually? Okay, so first you'll have a batch of data that goes into this model. And this batch goes into this first layer, and we'll call this a modified layer here as an imprint module. And what's in this layer is there is a linear layer. And in this linear layer, basically all the rows compute the same function. And in the simplest case, you can think that all, for example, for pictures, all the rows compute the brightness of these pictures. So all the rows are just 1 over n, where n is the number of pixels. Those are all the rows in this linear layer. So the output of this linear layer will be just, let's say this linear layer has a width of w, and the output of this linear layer will be w computations of the brightness of these images. What we can then do, however, is to modify the biases of this layer so that the biases are ascending based on the mass that we think will happen in this layer. So what this means is that the lowest bias will be -10. So all images will go through this layer, and then the biases will go up, and then up until like the last bias is, let's say, +10. And why is this important? After the bias, there will be a ReLU activation, a nonlinear activation that thresholds all the negative values. So if we, sorry, small correction. I think I confused myself here for a second. But on the very right side we have -10, and on the very left side we have +10. So that here we add a large number, so we always are in the positive side of it. We never threshold here, and here we have -10, so we always threshold. But what this does is that basically we threshold the brightnesses, and then we can actually, but then we actually have multiple measurements. We actually have W many measurements of brightness that are all ascending. And what this means is that all our images can now be decomposed again. Because if you think about the whole system again, what we have here in this layer, what we have in the gradient of this layer, is the sum of the gradients of the inputs here. And the inputs here are all these images. So if we have lots of images, then the gradient of each row will be the sum of all these data points. So these will be unrecognizable. It will be a sum of, let's say, 50 to 100 images. But because we have this gating here, this will only be an accumulative sum. So the lowest row, the gradient there will be the sum over all images. Then the next row will be the sum over all images, except for the image that has a brightness smaller than, let's say, -9.5. If this is this bias row here, then the next one will be -9, 8, 7, 6, 5. So we'll go through all this. So we have this cumulative sum basically constructed in this neural network. And then what we can do is we just have to subtract, and to find the image that has a brightness between, let's say, 0.5 and 0, we just have to subtract these two rows. And now if these rows are fine enough, then we can actually recover single data points from the average. And this basically is a way to break a multi-party computation here, because we actually compute a large sum, but we use our layers to disentangle the sum again. It's a spinning structure. And what this does in practice is that if we have a large batch of images, like say we have this group of images that we put through a neural network, and usually this is so large that this could not be recovered by another attack. But if we have this modified layer and we push these images through, then we can actually recover most of these images with this attack. And here you see that the attack, these images are, by the way, sorted. But what you see is that the attack actually works very often. And when the attack doesn't work, for example, here, you see that this is a very natural failure case where there were actually two images with a brightness value in this bin. So that here we recover only the average. And then you can easily think that if we only had one bin, then we would cover the entire average and we would be private. But here we actually have 128 bins and we recover a lot of data. So this is this attack. But what's the minimal scenario in which this works? And using corollary is that the minimal scenario in which this works is actually just a linear layer of width 2. And this is because if we want to recover only a single image, all we need are 2 bins or 2 rows, basically. We'll just have one row that sums up all the images up to our target brightness value, and another row that sums up all the images up to our target brightness value plus epsilon. And then we can have these 2 rows, get the gradients, subtract them again, and recover the data. And this works surprisingly well. For example, here, this is an image from the same test, but here we have a batch size of 32,768, which is pretty much as much as like I was content to wait for on our system to aggregate. But basically, this is a super large batch size. The gradient is averaged over all these data points. But with this modified linear layer of width 2, we can still recover this image to basically full precision. The only thing that would stop this attack eventually is if we aggregate so many data points that with floating precision, we couldn't do this computation anymore, which might be like 60, I don't know, maybe 100,000 images. It's not really clear. But even 30,000 is far outside the range of what's usually common in federated learning systems as an averaging, even with secure aggregation. But of course, these were, yeah.
Yeah, and also just a silly question. So the linear layer is itself is like constant, for instance, like doesn't.
Doing this in the system here.
Yes. So this first linear layer, this W that you insert, it typically can be constant, for instance, right? So. Or,
I guess you're asking about if the user has a federated averaging where the user does multiple updates.
No. Sorry, if you go back, I guess my question comes a bit late. But if you go back to your image of the attack where you insert the layer, this linear layer that you input and that you give. Okay, it doesn't really matter actually. If it's inserted at least at the beginning, it doesn't really matter what are the actual values of this linear layer because.
Yeah, but I mean, like really, the values of this layer are under the server control. So the server sets these values, sends them to the user, and after like some user updates, these values will have changed, but the server can just disregard the changes to these values.
Yes. So what I mean is that there is no particular values that these parameters in this layer should take, right? For the attack to work.
Yeah, I mean, or rather, like, I mean, they have to like measure. They have to measure this function basically. Like, if this is brightness, then these values have to measure brightness.
Right.
But there could be another function. Like, there could be any function.
Yeah, for
you
which
want to measure.
You can distinguish.
Yeah, exactly.
Okay.
Okay. Right. So this was model architectures. But of course, what if the model architecture cannot be changed? It seems like an easy fix to these sort of problems. And it actually might be relatively realistic. For example, if the model architecture is actually fixed, as it is usually, especially on current hardware, what you would usually do is that you would choose a model architecture, and then this model architecture would be compiled by the server. And if this process is supervised and vetted, then there'll only be like some compiled architectures on the user device that can't be changed with a new update. So here, the architecture is fixed. And the question is, do these attacks still work? And in this way, though, if we look at attacks now that are only malicious parameters, then these attacks can also only be applied. These attacks can be deployed anytime, even when the architecture is fixed. So sorry. These malicious parameter update attacks could be applied anytime, even if the architecture is fixed. And what's more interesting about these attacks is that these attacks are also very ephemeral, meaning that if the attack is only in the update parameters, then the server can send malicious update parameters to a group of users, run the attack, and then immediately overwrite these with benign parameters. And there's no trace of this attack really, because the attack is only in the parameters that are exchanged by users and server, which are overwritten very quickly and usually not stored. And so I'll talk about two variants of this attack that we found interesting recently. One is what we call phishing for user data. And what phishing really is that this is a variant of the attack you've seen previously for a malicious model, but trying to apply this to an arbitrary model that has arbitrary features. And the idea here is that usually there's a group of features that are all averaged. And now what we're really trying to do in this talk is we're trying to cut these features basically. In the same way that for the malicious architecture, we try to cut off two parts. Here we try to cut off the features of one user from all the others. And the simple strategy, I think where this makes a lot of intuitive sense, is if the server knew that a user had only one image from one class, and let's say 999 images from another class. This is sort of the simplest sort of choice scenario to think about this. But in this scenario where the user has only one image from this one class and a bunch of images from other classes, there the server can just disable the other classes basically in the model architecture, in the last layer of the model that classifies these features. All the other classes can be disabled. And then only this one class remains, and there'll be a gradient that is large only for this one class. But what's in a more general setting? In a more general setting, I'm going to talk about two variants of this. So one is a variant in cross-device. And to just update what I mean by cross-device. In cross-device, you think that there will be many users, but no user is queried twice by the server, and the users cannot be identified by the server, really. So in this scenario, how would we do this attack even if we didn't know the classes? So what the server could do in this scenario is to estimate the distribution of one feature that users have from a bunch of other users. And then the server can move the decision boundary of their model to exclude data from one user, and by a probabilistic argument, likely recover data from one of the users in the group, because there will be a single data point that dominates everything. I should probably go more into detail on this. I feel like I'm missing a slide here. So let me go back to this and be more detailed about this. So what's going on here is that, so we have a decision boundary in this model. Like our model has decision boundaries that separate classes. But these decision boundaries are entirely controlled by the model, and especially by the last layer of the model. So what the server can do is the server can move these decision boundaries around. And as soon as the server can measure basically this distribution, then the server can move the decision boundary around to exclude one user, probabilistically. The server won't know which user to attack. And this works in a way that the server estimates this function, and for cross-device, the server estimates this function from other users. And then the server has an idea where usual features lie from this class and this group of users. Features usually lie, for example, here on this curve. But once the server knows where the features lie, then the server can move the decision boundary until it is likely that all users are excluded, except for this one guy here. And if this is the only image that is excluded, then this will be the only image that's misclassified, and this will have a wrong gradient and a very large signal. And all the images that are all the other images in here will be correctly classified and have a very small gradient. And actually, the model will be modified in such a way that all images have a very small gradient, except for the target image that will be cut off. And then when we average all the gradients, this will be an attack as if there was just one image in the gradient. And then once there's just one image in the gradient, then we'll run the attacks from the honest but curious setting again. So this is basically this picture. So in the normal honest but curious scenario on top here, this is a batch of 32 where you couldn't recover really any of these images. This is a bunch of shark images. You can't recover anything here because the aggregation breaks the optimization-based attack. But if we just try to fish out this one image, then we can recover only one image from one of the users, but we can recover this one image almost perfectly. And this is this phishing attack, basically. Here, the server can't really target any of the users, but they can skim off random data points from users in general. And if you think that, for example, this might be an application that has hundreds or thousands of users, or any large number you want, you could do the tech example I have, like, oh, we have millions of users, then you see that there can be a lot of data gained from these attacks, even if it's not really clear where it comes from. So that was cross-device, and a variant of this is cross-silo. In a cross-silo, in our understanding, we'll only have a few users, let's say only 100 or less. Each user has a lot of data, but each user is uniquely identifiable, and the server can actually query these unique users repeatedly. And this actually breaks the assumptions from the previous case, because in the previous case, we used lots of other users to estimate the feature distribution. Here, this won't work as well, because here there are only so few users. So the question is, does the attack still work here? And the attack actually still works here by the simple trick that the server can actually just query a single user multiple times to cut off the data points. So basically, the idea is the server queries one of the users who has, let's say, 10,000 images, and the server figures out the mean feature from this user, because the server can always recover the mean. The server can just never recover individual features. So the server recovers the mean feature, then moves the decision boundary to cut off at the mean feature, and then the server can send an update model where all the mean features are removed. Then the server updates again, and again. And this is sort of a binary tree that's spent here. And I guess, as you guys know from algorithm theory, if we have this binary tree, then we can actually find a single point in very few queries. Even if we have 10,000 images in this batch, we only need 13 queries, roughly, to extract a single data point. Because basically, every time we see an average, we cut it in a strategy where the user can be queried multiple times. So here, this user was queried 13 times, and then the aggregate on the user side was resolved into a single data point that can be attacked there. So this is the way to run this attack if the server is allowed multiple queries. And then here are some more pictures of this, where we actually had, we put in some fish emojis here over the actual faces of people, because this is ImageNet, and ImageNet actually has a lot of actual faces which can be recovered here. But this is a batch just 256, which this would be hard or impossible for any other attack, for an honest attack. But here this still works by fishing for these images. And of course, we're being slightly cheeky here by also showing fish images. Okay, so that was one scenario where we think malicious parameters were interesting. Another one that we think is interesting is language, which I'm going to go briefly into. Well, we have a bit of time. So on language data, this is an interesting correlate to this, because language data has some interesting features. In language data, we have very expressive models. For example, we have these transformer models, and this will be set up about transformer models. These transformer models are very expressive, so they can encode many functions. On the other hand, though, language data is also very constrained, because we know from the outset that there will be only 50,000 words possible in the vocabulary, because these are agreed upon by the user and the server. So the attack only has to figure out which of the 50,000 words was used in the sentence from the user, and in which order were the words used. And we'll describe an attack that can actually do this. This attack is a bit more involved, but it basically revolves around the previous binning trick that we talked about. So here, what we can do is we can use the linear layers of a transformer architecture, because these transformer architectures, they alternate between a attention block and a feed-forward block. And we'll use this feed-forward block to run the same attack that we saw previously with the binning tricks. So we include these bins in these blocks, and then we can recover the inputs to these blocks. And what this will mean will be that I'm being very brief here, and I'll encourage you to look at the paper for more details. This actually applies to all the things I talked about. This is like a very high level talk here, but there are a lot more details in these papers that I didn't want to go into in this talk. Basically, we can bin these features and get the features, and so but these will be embeddings from all the incomers, which will be the sums of the token embedding and the position embedding. So we can recover all those. But then we just need to correlate these with our known token embeddings and our known position embeddings. So that will give us single words. And then we can use attention to also figure out which sentence a word comes from. Or sentence here rather means which batch a word comes from. We can use attention to figure that out. And then we use all our other layers, and then we'll actually disable all our other layers, so that no information is mixed, and we can actually repeat this attack in every layer of the transformer. So we'll actually, we don't need to have a single linear layer to run this attack, but we'll actually run this attack on all the linear layers of the model combined. And yeah, I'm maybe being too brief here, but what we basically can do is once we have these embeddings, then we can correlate these with our known embeddings and then figure out the words. And what we like about this attack is that this is an attack that works actually quite well. But here this attack only works with simple statistical analysis. So here we really just only need to compute all the tokens. And then we just run like just a basic matching and correlation analysis. And we just figure out which of the recovered rows just matches one of the tokens in our known vocabulary. And here are some examples with batch size 16, length 512. What's interesting about this attack is that this attack is actually accurate perfectly whenever it works. And whenever it doesn't work, the words are actually random. Or, sorry, the words are randomly permuted. So we still recover all the words that the user sent, but all the words that we couldn't recover are actually permuted in random ways that the attack cannot figure out here. And this attack works for a range of language models, for BirdGPT, and also for some small transformers that are actually used for language models. And in some scenarios, this can actually recover several thousand tokens from a user update. And we highlight like several thousand tokens here because this is a scenario where this can be interesting. This is actually close to some systems that have been run in practice. There have been some applications, although with LCMs, so not exactly transformers here, where people actually have run these systems with about, let's say, 500 sentences per user. And with 500 sentences with, I think it's also like 4 words. So there we have 2,000 tokens, and this attack is on the same level. You could recover 2,000 tokens with this attack. So I guess like in hindsight, you could think that some of these scenarios might have not been secure. And yeah, to round this out, of course, this were like just some variants of this threat model of malicious servers. There's a bunch of other interesting work that I want to highlight here. For example, there's work on machine learning by eluding secure aggregation, where people actually use the server to send a different model to every user, to identify the users and to break them. And there are also attacks that use side channel information to recover the users. And so these are other ways to use server information maliciously, for example, to metadata. And where really the takeaway is that many components of these FL systems can have unexpected security risks that we couldn't anticipate beforehand. So it really makes sense to think about these systems very clearly before we deploy them, especially if this is very vulnerable data. Yeah, but what about defenses, of course? And there's been a lot of defense in the literature, but I think my slide here is always just provable local differential privacy. And there's some reasons for this. So all the attacks I described are still bound by provable local differential privacy. If the update that's sent by a user has been made differentially private on the user side, and this is important because we don't trust the server here in this scenario, then this protects the privacy. And for all these attacks, I guess this is sort of like by definition, for all these attacks, as we increase the differential privacy coefficients, or rather lower them, the effectiveness of all these attacks steadily decreases. For example, the last attack I showed you was based on correlations between the breach data and the known tokens. But as we add more gradient noise to these breach data points, it becomes slowly harder and harder to run the correlation until the attacker cannot match the words again, and then the attack fails. Of course, differential privacy reduces model performance, can have some fairness implications, and is hard to tune. But to us, so far, this is the central defense that should be run to defend against these attacks. Yeah. If you want to look at some of these experiments that we just described, we also have some code online with an open source framework that you can install. And let us know if you have any questions also about the code. So for conclusions, we want to highlight that federated learning by itself is not a privacy mechanism. The privacy in federated learning really comes from everything that we use around it. That we use differential privacy combined with a large number of aggregations, because running only secure aggregation with no differential privacy can be attacked if it's a malicious server. And a lot of this talk was about large ML models, and this is because these large ML models leave a lot of room for attacks. And the server updates are basically untrusted code, and because these models are so expressive, the server can basically reprogram the models to run a lot of functions, and also functions that can actually recover user data. And we think applications have to be carefully designed to rule out all possible attacks. Yeah, thank you so much. And further questions and comments?
Thanks a lot. Very nice talk. So yeah, it's time to take some questions. So again, in the audience, if you have some questions, you can type them in the chat or raise your hand. Just to let you know, I will have to leave essentially in 10 minutes for another meeting, but I think if it goes a bit longer, Samuel is fine also to kind of keep up the Q&A going if needed. But I think I still have like 10 minutes. So maybe while people think about the questions, maybe I have one. Or maybe it's more of a confirmation or comment. So whether everything that you described kind of works indeed not only for one local update, but multiple local updates, which I guess still amounts to some kind of summer gradients, but puts some maybe weights that might be a little bit different in the end, depending on whether the point was kind of used early or last, right? So can you say a little bit about that and maybe the impact that it has on the attack?
Yeah.
Or the attacks,
so,
actually.
Yeah. So I think the simplest case thing about this is about this malicious architecture attack, where we actually have these layers introduced. And there, how federated averaging works depends a lot on how it's implemented. For example, who controls the learning rate on the client side? If the client side learning rate is very small, or it can be set to 0 or near 0 from the attacker side, then this is actually a federated SGG again. And so this is sort of like a side channel attack to run SGG again. If the learning rate is fixed and cannot be changed, then the server can try to rescale the layers so that the gradients in this layer are actually very small and don't change a lot, because the server controls the layers or can. And now we're making it more complicated, right? But if we allow for changes, then we can have another layer before this, where we try to downscale this layer, and we can upscale it later. So we try to reduce the gradients on this layer so that there'll be less changes. If those two things are still not possible, then federated averaging does diminish these attacks, because federated averaging leads to sort of a drift in these layers. So the server initially instantiates all these rows with the target function, but as the user trains for several steps, these layers drift to somewhere else. And then depending on how many layers there are, some of them will drift faster or slower, and they'll collide more often. And this will diminish the attack. But this is sort of how federated averaging works in this or against this attack.
I see.
Is that if learning rate is fixed and if the gradients are large enough, then these layers will drift away. And there's some ideas on like whether this is necessary, and I'm not sure if this is like a necessary feature of this or it's just a specific attack. There could be attacks that sort of anticipate this drift, but we haven't figured those out, and we're not sure if but these could be conceivable, but we haven't figured out if they are possible.
I see. So typically the results that you have shown, they are in the end for more like single updates, or you do this adaptation for multiple local updates?
Yeah, I've shown most examples here for single updates, but we also have examples, for example, in the paper on robbing the Fed, we also have examples for federated averaging with I think like 4 or 5 update steps. Okay. Where you see that, like, for example, here, like most of the bins still work and the gradients are relatively small, but you see that like a few bins sort of like fall off the radar and then mix data. And
So you can still see it as some form of defense, although maybe not such an effective one.
Maybe not such an effective one, but or in the sense that if you had like, I don't know, it depends so much on the learning rate on the user side. But if the user, and this is sort of goes against, right, the user can't go away too far from the central model usually, even for a benign update. But of course, the further the user is allowed to go away from the benign model, the more they'll break this attack. Benign model is a bit of a weird way to put it here, but like the further the user can go away from the central model, the more this attack is broken. Yeah, with an averaging scheme.
Maybe I would have two following questions on this. So does it mean that what you described, like when you described the thread average, like when you use thread averaging, maybe the attack is not that much efficient, but maybe like as you converge, right, like the gradients get smaller and smaller. So even with the many local steps, you don't get that much drift. So can it be the case that actually close to the convergence, then the actually attack can be very efficient?
Yeah, that's another point. Another way to just reduce the gradients would just be to run the attack later in training. Yeah, that's a good point.
Yeah. So did you kind of like try that? Because I guess that could be quite interesting, right? Or you always run it like after initialization, the attack?
Let me think about it. I think we ran this both ways, and it didn't matter too much. But for us, like so much more of the scale was changed by just changing the layer afterwards, the layer beforehand. Like you can change the gradient scales by having a low loss overall, but you could also change the layers before and after, just pull down on the gradients and just rescale these layers. And this has a similar effect to waiting to train longer.
And maybe one other clarification question. So when you were saying about this, like how to filter out like certain features or certain data points, you were saying like moving boundary. So is it some like, how exactly do you move it? Is it like somehow you updating the weight such that the gradient doesn't, like gradient for those data points that you kind of not very much interested in will be very small, or how exactly like this is done?
Yeah,
something I'm kind of curious about.
Yeah. I've been very brief about that, and we have more details in the paper. How this basically works is that there's a target, a feature, and a target class basically, and for that we'll have a very large gradient. For example, we can do that by setting the bias for that row to, let's say, plus 1000 in the last layer of this classification module. So this will have a sorry, let me think about it again. We set all the other rows to a very large bias. So if we set all the other rows in our last layer to, let's say, plus 1000, then the prediction will be very likely not the class that we're looking for. And this means that the class that we're looking, like the row that we're looking for, will produce a very large gradient. Because no matter what the user data is, it will always be misclassified into one of the other classes. And all the other classes will be classified correctly, randomly as one of them. So in this way, we sort of induce a very large gradient on the user. And then this was the class side. This was the last layer. And then we can also, because the row depends on all the features, like the row is like let's say 128 features of the input to this linear layer. There we can single out one of the features that we want to attack when we run this attack on, and we set all the other features to 0. And this is how this is sort of set up. And we'll have more details in the paper about this.
Thank you.
Basically, this is like setting all the biases to a very large value for all the other things, and so in this way trying to increase the gradient norm for the thing that the attacker wants to attack. Maybe something that I should also say about these attacks is that there's also another defense that I didn't talk about a lot in this talk, but just like very sort of like comes to mind very quickly. And that's like for some of these changes, you could find these by inspection. Like for example, for the binning, you could find, okay, all the rows have the same function. or here you can find, oh, you included like a plus 1000 in this last layer. This is clearly not normal. So these inspections on the outset, these are like very enticing defenses to us, but we're very careful about these as like a general defense, because in the end, you can always, with inspection, you can only find things that are basically, I mean, you can basically only have some rules. Let's say the rule is like, okay, no layer can have the same function in the same rows 100 times. So that's a rule, and that defends against that attack. But these models are very expressive. So there can be many attacks in different scenarios. So we're always very careful about these very specialized inspection rules, because on a user side, in the end, this has to be automated. There has to be a user app that's open source and deployed on the user side and inspected. And the user can't really look at these parameters. Even if like we as like research, we could like, okay, download the parameters and look at them. These defenses have to work even if the user is unaware, and if the user only has their own phone. And basically on the server side, we would filter some of these out by, for example, by outlier detection. But on the user side, the user only has their own device, and they can't really communicate with all the others. And their sort of outlier detection is much harder. So that's why we're like much bigger fans of these general individual privacy defenses, because these will work against any type of like attack. There are generic defenses in that way. Yeah, that was sort of a longer like about perimeter inspection, longer diatribe.
Maybe just before I leave, I can follow up on this, since you mentioned DP. So okay, being someone who works a lot on DP, I'm also all convinced about DP being a great defense. But you also mentioned about the costs, okay, that can be associated with DP. What people observe though in practice in other settings is that when you're trying to defend against concrete attacks, because there is usually a gap between concrete attacks and kind of the worst case view that is taken by DP, that sometimes taking parameters for DP that do not correspond to a very meaningful theoretical protection can still be very effective in protecting against attacks. So I was a bit wondering whether you observed that or not. So you have to actually add a lot of noise, you know, to defend decently against these attacks, or maybe in the end only a little bit of noise makes it already significantly harder. I'm a bit curious about that.
Mm-hmm. Yeah, it's actually a hard question to answer, right? It depends so much on like what's a good amount of noise or what's a reasonable amount of noise.
I mean, in terms of epsilon, I guess so. You know, if you take epsilon equal 50, for instance, that would be considered, and you know, calibrate the noise based on this, that would be considered almost like a void, maybe privacy guarantee from the theoretical point of view. But you sometimes see in practice, this can still like help a lot against concrete attacks. So
yeah, I mean, here basically this doesn't do, like a lot of these attacks have the effect that they sort of continuously get worse as there's more noise added. For example, for the binning, we have these rows that compute, and so the only thing that happens if there's gradient noise added, so the cumulative sum will still be there. There will just be noise on all the rows. And so if you run the attack, the central effect will happen that the gradient noise is added to the input data. So it's sort of converted from like gradient noise to input noise. And you could, if you think about this, like just adding a small amount of input noise to images still breaches their privacy. And like, so the central mechanism of the attack is just like gets continuously worse as we add noise.
okay.
And like, maybe another way to think about this is like especially interesting is this for the language model attack, because that attack is only based on correlations. And then it's like, okay, even if we add noise to this measured vector that we sort of retrieve on the gradient, if there's a bit of noise added, then the correlations are still good enough to recover the text perfectly. And then we have to add enough noise that the correlation between the gradient and the known token embedding actually breaks. And this usually continues. This is like a smooth curve. So it's hard to move. Yeah, it's hard to move. It's like for me, for us, it's always like you can add enough noise and then it breaks. But it's for us like very hard to say like for. I mean, there's like usually like a larger study. Like here's our application, and this application can like tolerate so much noise. Will this amount of noise also defend against this attack? this is usually a larger study where we're like, okay, here's this amount of noise and detect kind of works, and here's this amount of noise, detect kind of works. Also, I mean, in the end, like what noise level is acceptable does depend on the application a lot, right?
Right. Yeah. I was curious whether you need to add noise to the point that you really deteriorate accuracy significantly, or maybe, where the threshold is compared to where the accuracy of the task starts being really affected. So maybe there is a sweet spot, or maybe not. That will depend. Yes, obviously also on the task. Okay.
Yeah.
Thanks a lot. I guess I really have to go now.
Yeah. Thank you for the questions.
Yeah, and thanks a lot for the talk. It's very nice, and I will also look at the paper to understand a bit more formally the attacks. But it was nice to get the main ideas and the motivation. So thanks a lot.
Yeah.